My name is Patel, and I will be discussing our Lab 2 over an object falling in motion. Before I begin, we need to first understand key concepts regarding this lab. Firstly, we have Newton's second law, which states that the net force of an object is the change in momentum divided by the change in time, or force equals mass times acceleration. Deriving these equations can lead to the position update formula, which updates the object's position over the change in time, and the velocity update formula, which updates the object's velocity over the change in time. Another key concept is the gravitational force near Earth's surface. The formula is the product of the object's mass and the acceleration due to gravity. The magnitude of the gravitational force of the object due to the Earth is the product of the gravitational constant g and both of the masses divided by the radius squared. We can derive the acceleration due to gravity using the formula, leading us to finding the g value, that being 9.8 meters per second squared. Next, we need to understand that there will be a drag force acting on the object. Since there are air particles moving in the atmosphere, this means that it will slow the object down, meaning that it opposes gravity in the opposite direction. The formula is the product of the drag coefficient b and the velocity squared. In this lab, the drag force is in a positive y direction, the system is the paper ball, and the surroundings are everything else. The goals of this experiment is to observe the motion of a falling object as it falls at rest using tracker. We will then compare it to the two computational models, one that includes drag force while the other does not. We will be using GlowScript and Python in order to model unmodeled data. A key assumption is that we will only be including the motion in the y-axis. This is a tracker video. The graph shows the position time graph for the paper ball motion. Since the paper ball is falling down, the graph will be sloped downwards and appear parabolic due to the acceleration of gravity. Here is the data from tracker. The diameter of mass is shown above, and the change in time is equal to 0.6 seconds. The ball's initial and final position is shown below, and the initial velocity is 0 since the object was dropped from rest. Next, we coded our findings in Python using a website called GlowScript. This snippet of code attached shows the paper ball mass and its initial position and velocity, which were stated in the previous slide. Delta t is equal to 0.017 since the video was recorded in 60 fps, meaning that every 60th frame the object's motion was being recorded. Since there is no drag force, the b value is 0. G is still equal to 9.8. Next, the while loop, which updates the object's position and velocity using both the formulas mentioned in the beginning slides. As you can see, the only force that's acting on this model is the force of gravity, so that will be included in the net force equation. The code to update the object's position and velocity is shown below. Notice how similar these codes look to the formulas below. Then delta t is added again to t until the time reaches the final observation time, that being 0.6 seconds. Now we have the code to include the drag force. Notice that the code is essentially the same, however we have to include a non-zero number into our b value to include drag force. Since we're including the drag force, the net force will be equal to the magnitude of this drag force added to the weight of the paper ball. This code is shown here, and the formula for the drag force and its respective variable equation is shown here. The position and velocity update formulas remains the same. These are the results from GlowScript. The one on the left is a model with no drag force, while the one on the right has drag force. This is the graph for the observed motion of the paper ball versus the predicted motion of the paper ball and a position time graph. Since the object was moving downwards, the graph would be sloped downwards and it'd be in a parabolic shape since there was acceleration acting on the object. The x-axis is a time in seconds and the y-axis is position in meters. As a result, all three models were essentially following the same path throughout most of the object's motion. However, towards the end, we see that the computational model that did not account for the drag force differed slightly from the other two models. This indicates that there is some force acting in the opposite direction of gravity, therefore slowing the object down. This means that the model that includes the drag force is a better model for predicting the object's motion. Some possible errors include tracker errors since when trying to do the point and mass function, the white ball blended into the background, making it harder to pinpoint the exact location of it. Also, rounding errors and not accounting for motion being in the x direction were all factors in possible errors in this experiment. Some additional questions that may be asked are, which model predicts the terminal velocity better? That would be the drag force model on the right, since its parabolic shape indicates that it doesn't follow a constant velocity, meaning that it will eventually become a straight line resulting in terminal velocity. Another question is, would the terminal velocity be the same if the object was going downwards? it would still be the same but only occur at an earlier time. I proved this by altering the code and added initial velocity, and as you can see in the graph, it looks essentially the same. However, it looks like the graph will reach terminal velocity quicker than the one shown on the right.